everyone! Now let's learn how to convert between different numbering systems. First, we'll learn how to convert other number systems into the decimal system. The conversion to decimal has a clear mathematical formula called the expanded form of place values. Here, k represents the base. So for a binary number s, k equals 2, and for a hex number s, k equals 16. The index I indicates the position, where the ones place corresponds to I equals 0, the tens place to I equals 1, and so on. We typically use terms like ones place, tens place, hundreds place, and thousands place to refer to a number's position, right? In this formula, the ones place corresponds to I equals 0, which is the 0th position. Following the same logic, the tens place corresponds to I equals 1, which is the first position. C represents the number in the ith position. This formula allows us to expand any number in any numbering system into a polynomial sum, and then further calculate the corresponding decimal value. This is the method for converting between different number bases and decimal. Let's illustrate this with two examples. The first example is converting a binary number to decimal, like converting 1101, 101 to decimal. First, expand this number into a polynomial using the expanded form of place values. Here, k equals 2, and the integer part ranges from the 0th power up to the 2nd power. S0 corresponds to the number 1 in the 0th position. S1 corresponds to the number 0 in the first position. S2 corresponds to the number 1 in the second position. And S3 corresponds to the number 1 in the third position. The place values for the fractional part range from the first power down to the third power. S-1 corresponds to the number 1 in the first position after the decimal point. S-2 corresponds to the number 0 in the second position after the decimal point. And S-3 corresponds to the number 1 in the third position after the decimal point. Finally, performing the sum operation, we can work out that 1101, 101 in decimal is 13.625. The second example is converting the hex system to the decimal system. In this case, k equals 16. 0 corresponds to the number 4 in the 0th position of the integer part, and S1 corresponds to the number 6 in the first position of the integer part. -1 corresponds to the letter C in the first position of the fractional part. So we can work out that the hex number 64, C represents the decimal number 107.5 next. Let's learn about converting between the binary system and the hex system. Converting between the binary system and the hex system can be done through table lookup. We can group the 4 places of the binary system together to represent one place in the hex system. For example, the 4-place binary combination of 000 can be seen as representing 10 in the hex system. How many different combinations are there for the 4 places in the binary system? The answer is 16 combinations, which correspond to the 16 forms in the hex system from 0 to F. The numbers 0 through 9 are the standard digits. Once you get to 10, there are no more corresponding digits. So we use the uppercase letters A through F to represent numbers 10 through 15 in the hex system. This allows you to easily convert between the binary system and the hex system by looking up the corresponding values in a conversion table. With practice, you'll be able to do these conversions quickly in your head. Let's walk through some specific examples to illustrate this. Let's start by looking at an example of converting a binary number to hex. The binary number is 1111000001, 101001. Starting from the decimal point and moving left, we'll group the digits into sets of 4, totally 3 sets here. For any groups that don't have 4 places, we'll pad them with leading zeros to make them a 4-place number. Looking at each group one by one, we can look up the corresponding hex values. 0001 corresponds to the hex number 11. 11100 corresponds to C, and 0011 corresponds to 3. This completes the conversion of the integer part. No, let's look at the fractional part. Moving right from the decimal point, we'll also group the digits into sets of 4, padding with zeros if needed. We can see that 1010 corresponds to the hex number A, and 0100 corresponds to 4. Therefore, this binary number can be converted to the hex number 3, C1A4. Let's look at another example of converting from hex to binary. Say we have the number FEE05H. Also, starting from the decimal point, we will convert each hex number or letter into a 4-place binary number. First, let's convert the integer part. E may be converted to the binary number 1110, and F may be converted to 11111. Next, let's convert the fractional part. After the decimal point, 0 may be converted to the binary number 000, and 5 may be converted to the binary number 0101. So for this number, FEE05H, we get 11111111, 0111, 000001, 0101. Finally, let's look at how to convert a decimal system to the binary number and the hex system, which is the challenging part of this key point. To break through this challenging part, let's first simplify the problem and start with the easier aspects. Let's first look at how a decimal number may be converted to the binary number. Since the decimal system has an integer part and a fractional part, and the conversion methods for these two parts are different, for the sake of simplification, let's first convert the integer part. The rule for converting the integer part is to divide the decimal number by 2. Take the remainder and repeat this process until the quotient becomes 0. To illustrate, let's say we need to convert the decimal number 254 to the binary number. We will perform a series of divide by 2 operations, recording the quotient and remainder at each step until the quotient becomes 0. For this example, dividing 254 by 2 results in a quotient of 120, 7 and a remainder of 0. We record this. Next, we divide the quotient of 127 by 2, getting a quotient of 63 and a remainder of 1. We continue this process, dividing the quotient by 2 each time and recording the remainder until the quotient becomes 1. At this point, dividing 1 by 2 results in a quotient of 0 and a remainder of 1. This concludes the operation. At this point, we can obtain the binary number. This binary number is composed of the remainders, where the first remainder obtained is the lowest order, and the last remainder is the highest order. Therefore, when we write this binary number from the high order position to the low order position, we are actually writing from bottom to top. So the binary number for 254 is 111110. This is the result of the conversion. In summary, the process of converting a decimal number to its binary number representation is as follows. First, divide the decimal number by 2, recording the quotient and remainder. Then continue dividing the quotient by 2, again recording the quotient and remainder, until the quotient becomes 0. This concludes the operation. The final binary number is constructed by writing out the remainders in reverse order, from the last remainder to the first. Next, let's look at how to convert the fractional part. The process of converting the fractional part of a decimal number to binary is different from the integer part. For the fractional part, we multiply by 2 and round the result to the nearest integer to obtain the next digit in the binary representation. After performing multiple multiplications by 2 and rounding, there are 2 possible outcomes. 1. The fractional part becomes 0, in which case the conversion is complete. Or 2. The fractional part remains non-zero, in which case we can stop the calculation once we've reached the required precision level. For example, to convert the decimal number 0.125 to binary, we multiply the fractional part by 2 and round the result. 0.125x2 equals 0.25, and rounding 0.25 gives 0 as the first binary digit. We then continue this process, multiplying 0.25 by 2 to get 0.5, rounding to 0 as the second digit, and then multiplying 0.5 by 2 to get 1, with a rounded result of 1 as the final digit. The first rounded result is the highest order of the binary fractional part, and the last rounded result is the lowest order. So when we obtain the binary fractional part, we are essentially writing it out from top to bottom. Therefore, the binary number corresponding to 0.125 is 0.001. Now, let's look at a slightly more complex example, converting the decimal number 112.26 to binary. First, we'll convert the integer part. We take the integer part 112, divide it by 2, and record the quotient and remainder. After multiple such operations, the final quotient becomes 0, and the remainders written from bottom to top, left to right, are 111000. This concludes the conversion of the integer part. Now, let's move on to converting the fractional part. For the fractional part 0.26, we multiply it by 2 and round the result. We then continue this process, multiplying the remaining decimal and rounding. For a total of 4 operations, we find that the fractional part still does not become 0. Assuming the requirement is to be precise to 2 decimal places, the conversion result would be 0.01. Therefore, the final binary representation of 112.26 is 11100001. I would like to remind you that if the fractional part conversion requires multiple calculations, but the fractional part still does not become 0, the final result will have some error introduced during the conversion process. This error can be amplified or reduced as the calculation continues. Next, let's look at how to convert a decimal number to a hex number. The process of converting a decimal number to a hex number is similar to the method used to convert a decimal number to a binary one. It involves step-by-step calculations. For the integer part, always keep in mind the key difference is that we divide by 16 instead of 2, and the remainder can be a number from 0 to 15, not just 0 or 1. For the fractional part, we multiply by 16 and round the result, again obtaining an integer from 0 to 15. In summary, the method is the same as converting to binary, just replacing the base 2 with base 16. For example, to convert 301.6875 to hex, we first convert the integer part. We divide 301 by 16, getting a quotient of 18 and a remainder of 13. We then divide 18 by 16, getting a quotient of 1 and a remainder of 2. Finally, we divide 1 by 16, getting a quotient of 0 and a remainder of 1. Writing these remainders, keep in mind from bottom to top, gives the hex integer part as 12D. Now let's convert the fractional part. To convert 0.6875 to hex, we first multiply it by 16, which gives the result of 11 after rounding. Since the fractional part is now 0, the conversion of the fractional part is complete, and the final hex representation is 0b. Therefore, the full hex conversion of 301.6875 is 12 dBH. If you find the division by 16 and multiplication by 16 calculations too complex, there is another method you can use, that is, first convert the decimal number to binary, and then convert the binary number to hex. We have already covered the processes of converting from decimal to binary, and from binary to hex. You can choose the method that suits you best, based on your own preferences. This lesson covers a lot, so I recommend that you review the video repeatedly to deepen your understanding. In the next lesson, we will learn about the representation of unsigned numbers and signed numbers. See you next time.